Okay, today we're going to talk about another type of conic called an ellipse. We've already looked at circles and parabolas. So we're going to define an ellipse as a set of points, just like we did for a parabola. This time though, it's a set of points in a plane, the sum of whose distances from two distinct fixed points, called foci, is constant. So what I've done is I've set up a visual for you here in Geometry Sketchpad. And so we have 2 points. Each one's called a focus. Plural is foci, or some people pronounce it foci. And we're looking for, let's say I take a random point, and I measure the distance to this focus, and I measure the distance to this focus, and I add those distances together. Whatever that comes out to, I want all the other points whose distances to each of the focus winds up being the same. So, without going into too much detail, I've created a segment here AC that's 15 centimeters long. I want the total distance to be 15 centimeters. I could change that, that's just random. So now what I'm going to do is I'm going to take this focus and this length, and I'm going to construct a circle. And then I'm going to take the other focus, and this length, and construct another circle. And then I'm going to take the points where those circles intersect. Okay, so now if you look at this point here that I've just highlighted, the distance to this focus, that's a radius of the smaller circle, which right now is 5.43. And then the distance from the same point to the other focus is the radius of the other circle, which is 9.57. So those two distances together add up to 15. Now if I move this point B somewhere else along AC, that's going to change the radii of the circles, but still together they're going to add up to 15. So I want to look at these 2 points here and where they travel as I move B. And so those 2 points are showing us all the points in the plane that are going to be 15 centimeters away from both of the foci. To give you a better visual, let's go ahead and trace out these 2 points. This is the wow moment, so feel free to go ahead and say wow out loud. Ooh, wow. Let me make it a little easier for you to see. Let's set up an action button. Let's animate that point slowly. And that over here. There we go. So you can see when the circle gets, or when segment AB gets too big, it's not going to intersect the other circle. And likewise, when the circle with radius CB gets too big, it won't intersect the smaller circle. But their intersection will give us all the points that when you add up the distance from that point to each focus, it's going to be the same for every single point. And that's what an ellipse looks like. Okay, I'm going to come back to this picture in a little bit. Let's set it up for when I come back to it. There we go. Okay, so now let's familiarize ourselves with the terminology for all the parts of an ellipse. So we already know that the 2 fixed points are called, they're each called a focus, plural foci. And then if I take if I draw a line through the focus, through the foci, where that line intersects the ellipse, that segment there is going to hit the ellipse at these 2 points, and those are vertices. So those are the vertices of an ellipse. The middle, the midpoint of that is called the center, and the segment from one vertex to the other is referred to as the major axis. Major axis. So the foci and the vertices and the center are all on the major axis. Now if we draw another line through the center that's perpendicular to the major axis, that'll intersect the ellipse at 2 points, And that segment has a name, and it's called the minor axis. We don't have a special name for the 2 points, the 2 endpoints of the minor axis. So that's how we'll refer to them. I'll just say, what are the coordinates for the endpoints of the minor axis? Now we also have some measurements that are important. So the distance from the center to a vertex, that's always going to be referred to as A. So from the center over to the other vertex, that also has a length of A. The distance from the center to the endpoint, one of the endpoints of the minor axis, we're going to call B. And to the other end of the minor axis, that would also be B. And then finally, the distance from the center to either focus, we're going to call C. So A, B, and C will always refer to those specific measurements for any ellipse. Those aren't just random assignments for right now. So if, let's write this down. So the distance from the center to a vertex is A, which means from one vertex all the way to the other vertex would be A plus A, or 2A. The distance from the center to a focus is C. So the length of what sometimes you'll hear as the focal chord, or the segment connecting the foci, that has a length of C plus C, or 2C. And finally, the distance from the center to the endpoint of the minor axis is B. So the entire length of the minor axis will be B plus B, or 2B, or not 2B. All right, so that's all the things that you should be familiar with for the parts of an ellipse. You have to have that down before we can start talking about equations and graphing ellipses in the coordinate plane. Now there's one other important measurement, and that's referred to as eccentricity. And that doesn't mean how strange I am. That means the ratio of C to A. So remember, C is the distance from the center to the focus. A is the distance from the center to the vertex. And so let's go back and look at this picture for a second. So eccentricity is C over A. So C is this distance, and then A is that distance. So in an ellipse, A is always bigger than C. Sometimes it's a lot bigger, sometimes it's not a lot bigger at all. If C is close to the vertex, then C is almost as big as A. But if C is close to the center, then A is a lot bigger than C. So in any event, for this ratio, this fraction, when we do C over A, since C is always smaller, eccentricity is always going to be a number between 0 and 1. It'll never equal 1, it'll never equal 0. And so this number that we get between 0 and 1 for eccentricity, basically that tells us how circular the ellipse is. So let me go back to that sketch I had set up somewhere. There it is. And I'm going to move these a little bit. So first of all, let's get rid of the traces. We don't see those. Let's separate the foci a little bit more. Alright, let's erase those. Okay, so I moved them further apart. So in other words, I took the foci and I moved them away from the center, because the center is halfway between them. And so look what happens as I move them away. Our ellipse gets more oblong, or less circular. Okay, let's erase those. Now watch what happens when I move them really close to each other. Now remember, the center is right in between them, halfway in between. So now they're a lot closer to the center. So now that C value is a lot smaller. C is the distance from the center to the focus. And so that's a lot smaller than the distance to the vertex, which is A. So when C is a lot smaller, look what we get. I have to wait till it comes back around. There we go. And notice it's a lot more circular now than it was when the foci were further apart. So the closer they are to each other, the closer they get to the center, that means the smaller C value, scroll up here, as these get closer to the center, C gets smaller, and therefore the fraction C over A is getting smaller and closer to 0. So the closer eccentricity is to 0, the more circular your ellipse is. Okay. So let's look at one other relationship that's really important in order for us to be able to answer questions about ellipses. It turns out that a squared is equal to b squared plus c squared. A lot of times students get this confused because they think Pythagorean theorem. So you have to remember the picture. Out of a, b, and c in the picture, which one is always the biggest? Well, it has to be a. The major axis is always longer than the minor axis. So that's how we decide which one's major and minor. The major is always bigger. So that means that the center to a vertex, which is A, will always be bigger than center to an endpoint of the minor axis, which is B. And obviously A is bigger than C as well, so A is the biggest of those three. So that has to be the one that goes by itself in this, what you could think of as a Pythagorean identity. Okay, so it's not a squared equals b squared plus c squared anymore. That's only for a right triangle, where a and b are the legs. So where does this come from? Well, let me just show you quickly how we would get this. So let's say that, okay, all the points on this ellipse, we know that if we measure the distance to one focus and then the distance to the other focus and sum those together, we're going to get the same answer no matter where this point is. So that means from there, if I measure the distance, which are those two purple dashed lines, and add them together, that should be the same as if I measure the distance from that point to each focus and add them together. And so that's how we're going to figure out this identity. Alright, so what is the distance to each focus if my point is up at the top there? So in that case, we know that in this right triangle, the legs are C and B. So the hypotenuse is going to be the square root of b squared plus c squared. And so that's true for this length and for this length, because they're equal when I pick my point to be right up here at the top, the endpoint of the minor axis. Alright, so those together, if I add those distances together, I'm going to get 2 times the square root of b squared plus c squared. You won't have to recreate this when you're doing problems. I'm showing you this so that you can remember this equation. Alright, so that's the distance that's the sum of the distances to the foci. Now, what if I take this point and then move it over to here? Well, the distance to each of the foci should, when I add those together, should equal the purple that I just calculated. So now we have to figure out, well, if from the center to the vertex is A and the center to the focus is C, then wouldn't that make this distance A minus C? So the distance from the vertex to the closer focus is A minus C. And then what's the distance? Let me get rid of those. What's the distance from the vertex to the focus that's further away? Well, we know that part of it from here to here is A, and from here to here is C, so the total distance would be A plus C. And if I add those two distances together, that should equal the same as what I got when the point was up at the top of the ellipse. So when I add those, the C's cancel, and I get 2A. So that should also equal 2 times the square root of B squared plus C squared. Now I can divide both sides by 2, and then I can square both sides. And that's how we get A squared equals B squared plus C squared. Okay, now with that relationship, we can start talking about equations. So there's two basic equations for an ellipse, and it depends if the major axis is horizontal or vertical. And we're not going to worry about rotating axes. So for now, those are the only two types that we're going to be concerned with. So if you notice, it kind of reminds you of the equation of a circle, except in the denominators we don't have the same number. If A and B were the same number, then it would be the equation of a circle. So, which by the way would mean C is 0, and therefore the eccentricity is 0 and it's a circle. So if the center of our ellipse is HK, then if the, let's draw this in here, if the major axis is horizontal, then we're going to have this equation. And remember, A is bigger than B for an ellipse. On the other hand, if our major axis is vertical, there we go, then we're going to have, this is our equation. And notice the only difference is the denominators of our fraction. So basically when you look at the equation of an ellipse, it has to be x minus something squared over a number plus y minus something squared over a number equals 1. So we always want to make sure that it equals 1. And then what we have to do is look at the two denominators. And whichever one is bigger, is that underneath the x or underneath the y? If the bigger one is underneath the x, then we have major axis is horizontal. Save myself some writing. And if, on the other hand, if the bigger denominator is underneath the y term, then the major axis is going to be vertical. And so that's key in trying to figure out what the equation is going to be. Now, I have several examples, but I'm going to split this lesson up into two parts. So this is part 1, and I'm going to end this, and then you'll go to part 2, and I'll work through some examples and give you the assignment. So, if you need to, go back through and make sure you understand the labeling of all the terms and all the measurements A, B, and C before you're ready to start doing the examples.